So before we said that if there were no non-conservative forces, if all the forces were conservative in nature and internal to the system, we could say that the mechanical energy was conserved. But now, if there are forces from non-conservative things, well then, we can still say that the total energy is conserved if we take into account thermal energy, the fact that it warms things up, that the molecules start bouncing around faster. This will also allow us to accept the possibility of energy from external sources. So in this case, the total energy at the beginning, that's gravitational potential, elastic potential, and kinetic energy, plus whatever work is done by non-conservative forces, or it could also be work done on the system. So it could be from outside the system done on the system. Whatever things get, what we started with plus whatever got added equals what we end with. Potential energy from gravity at time 2, potential elastic energy at time 2, and kinetic energy at time 2. And with that, we'll be able to do a lot of problems. So let's talk about our strategies. The first thing we want to do is we want to choose our system. We want to make sure that we include all objects that we're interested in studying, and we need to list all the forces acting on or within our system. We're going to draw sequential diagrams. You can review that skill from 6.1, but basically we're going to draw what the situation looks like at the beginning and what it looks like at the end. We're going to identify our zero energy conditions, what we want to be considered to be the zero energy position. We're going to identify what non-conservative forces might be acting in the system. And then we'll write down the energy balance equation that the external work equals the total change in energy, which is the change in mechanical energy plus the change in energy from non-conservative sources. Or in some situations, if there's no outside, we can say the total energy at the beginning, potential plus kinetic, plus whatever work is done by non-conservative forces equals the total energy at the end. So here's an example where we can look at that. We've got an elevator of mass m and at height h above a spring right here. When the cable suddenly breaks, causing the elevator to plummet until it hits a safety spring, constant K, installed at the bottom of the shaft, the elevator bounces many times before coming to rest, with the spring compressed a distance s. A constant friction force of magnitude F acts on the elevator from the walls. What is the total distance traveled by the elevator, including all bounces? Okay, so here we've drawn the situation before. It's got gravitational potential energy because it's up. It doesn't have any spring potential energy because the spring is uncompressed. At the end, it's got a smaller gravitational potential energy because it's down. In fact, if I define this to be my 0 point, it'll be a negative. And it has some spring potential energy because the spring is compressed. However, it won't necessarily have the same total energy because some of the energy has gone into the various different bounces.